I'll just brief you through combination of lenses, and then we'll go on to other aspects in the same chapter. So, combination of lenses. So you know already that you have convex lens and concave lens. You can use two or more lenses in either an optical instrument or for your eyeglasses, or for anything like that. So you can have sometimes combination of lenses. Now, lenses sometimes, the combination of lenses can be put together, one after the other immediately, or sometimes they are spaced by a certain gap. Now, if they're put together, if thin lenses are just put together, then the focal length of the combination is just adding the powers up. Okay? If the lenses are put together like this, if this lens of focal length f1 is put together with the next one of focal length f2, 1 over focal length of the whole thing is going to be 1 over f1 plus 1 over f2. It's just going to be so what is 1 over f? It's the power of the whole thing. So power of the whole thing is going to be power of the first one plus power of the second one. And when you did those readings, you must have gone through power and all those things. What's power? It's a reciprocal of the focal length, but the focal length must be expressed in meters. You can't express in centimeters, you have to express it in meters. Then it's the power. So if you have this one's power, if the first lens has a power of +1 and the second one has a power of +2, then the whole thing has a power of +3. Yeah? So this is something that happens when you put the lenses together, stick them together. Now, if the lenses are separated, then things are different. If the lenses are separated, then you have to take one lens, work out the entire thing, find out where the image is found, then take that image as the object for the next lens, and then work it out once again. So let me solve this through an example. So let's say if you have a convex lens, and let's say this one's focal length is 40 centimeters. And imagine you're putting the object at 60 centimeters. Where's the image formed? Where's the image going to be formed for this lens? Now, before you do this, remember one more thing. If rays are converging and hitting somewhere to form an image, that will be a real image, correct? If rays are converging and really kind of hitting each other here, that will be a real image. If rays are diverging, they're not going to hit that side. If rays are diverging, that means these rays are appearing to come from somewhere, and that will become virtual. That will become a virtual image. Similarly, if you have a real object, now I have not spoken about objects as real or virtual, now we are talking about it. This is a real object. How do rays go from a real object? They go diverging. So from a real object, rays actually come out like this. Like this is a real object. How do the rays go from here to the lens? This way. So which is real? This is a real object. This object is real. Which means it's the focal length, the object distance is positive. Do you understand that? Now there may be a situation where you will have a virtual object. So when it comes, I'll let you know what it is. Now, don't worry about the real object and all that. In this case, just go ahead and find out where the image is formed. So if the rays are go from here, where is the image formed? So work out that one. 1 over f is equal to 1 over do plus 1 over di. 1 over 40, you can work in centimeters throughout, is equal to, and why I put it as 40, because this convex lens is a positive focal length. 1 over DO, it's a real object, and so it's 60 plus 1 over DI. So what is 1 over DI? Which is equal to 1 over 40 minus 1 over 60. So it's 2 over 240. So 1 over DI is this, therefore DI is 120. That means these rays are going to hit where? They're going to hit 120 centimeters away. Yeah. Now remember, these are not real ray diagrams, because ray diagrams you draw by taking the object and going parallel and all those. This is not a ray diagram. It is a ray diagram, but it is not something that we are drawing geometrically, following those rules. We know that it's going to hit at 120, therefore we're just taking the rays there. Okay? So if rays go from here, they should be going and touching here. How far is this? So the image will be formed there. What kind of image is that? Real. Because it's really hitting there. Now, let's say we have another lens. Yes?
How did you know it was real? Because it diverges in the beginning?
No, it's real because those rays are actually meeting at that point. So if I put a screen there, I should get the image on it.
Oh, okay.
Okay?
So how would it be divergent? How would it, like, you know how earlier you wrote real image and...
Real image will be like something that's formed straight away.
Like that?
Like this. Diverging means if the rays are going this way, they're not definitely going to meet anywhere. But they appear to come from somewhere. And we trace it back, and that distance is what's considered as virtual image distance. Okay, so in this case, so far everything is good. Now, let's say we put, suppose you put another convex lens here of focal length 60 centimeters, and that convex lens is placed at a distance of, let's say, 50 centimeters from the other lens. 50 centimeters. So first lens is here, the second lens is right there. Now, what is going to happen is this. Are these rays really going to go there? Are these rays going to continue going straight? No. So these rays are not going to go there. They would have gone there if this lens was not there, right? These would have gone there if this lens was not there in position. But because this lens is there, what is going to happen at this point is that it is going to suffer another refraction. It's going to suffer another refraction. So now let's work out the entire problem for this lens alone. We're going to solve this problem for this lens alone. So for this lens, what is the focal length? No, focal length. Positive, negative. It's positive 60, only for that lens. Don't worry about this at all now. For this lens, f is positive 60. What is DO for this lens?
110. That's 50.
Okay, so these are the rays coming onto the lens. Look, when these rays were coming onto this lens, we considered this distance to be our object distance, and we took it as a real object distance, correct? We took this distance as a real object distance because it was actually coming from here. But where are these coming from?
Doesn't the image formed by the first lens become the object of the second lens?
It is. But then we are interested in knowing what distance it is.
Is it negative 10?
These are rays coming onto this lens. and they are definitely not coming from a definite point on this side, but they appear to be hitting there. So what is the object distance for this lens? Yes,
Is it -70?
it is negative 70. Why? Because these are not definitely coming from this side, but they appear to be hitting here. They are appearing to be hitting here. How far is this distance? 70 centimeters.
How do you know that?
Because you know the whole distance is 120,
Oh,
and the distance between the lenses is 50, so that is 70. Do you get it? So these rays are coming from somewhere, not from a definite place. That is why we consider it as negative. Do you get it? Now these rays are coming from a definite place, so we consider that as a positive object. These rays are coming from somewhere. We don't know. That's why we consider that as a negative virtual. So for this lens, this becomes a virtual object. Get it? For this lens, this becomes a virtual object. But the same thing was a real image for the first lens. Yes. Wait, don't miss it. Urgent?
Yes.
Go. Now, question is, what is this? Now you start working with your equation. 1 over f is equal to 1 over dO plus 1 over di. And then just work it out. 1 over 60 is equal to 1 over negative 70 plus 1 over di. So 1 over di is equal to 1 over 60 plus 1 over 70. Because that minus sign comes up here, it's plus. So it becomes 420, 7 plus 6. Okay, so di is equal to 420 over 13. And it comes out a positive distance. How much is that?
32.3.
32? And it's a positive distance, which means it's a real image. So what exactly is going to happen is this. These rays would have gone there, but because of this convex lens, it converges further and hits at a distance of 32.3 centimeters. So finally, where is the image formed? It's right there. Make sense? So this is what you do for a combination of lenses. You just have to do one, and then you do the next, go. And you'll be able to figure out exactly where the image is formed. And now if you want to find the magnification of that image, you would do the magnification of the first one, and then find the magnification of the second one after the other. Yeah,
How many lenses keep on going? Like, is there
Yeah.
any sort of
any number. So if I keep one other lens, then this becomes the object for the next lens. It could be a real object, it could be a virtual object. If I really put an object here, if I put a lens over here, this becomes a real object for that lens. But if I put a lens over here, then that becomes a virtual object again. Right? So now you can put a concave lens. I'll try. So have you picked it up? Now if I'm just going to change this problem slightly, and I'm going to put a concave lens instead of a convex lens. If I put a concave lens instead of a convex lens, let's say the focal length of the concave lens is 60 centimeters. Now what's going to happen over here is that it's going to diverge because it's a diverging lens. It's going to diverge because it's a diverging lens. And so we do f is equal to negative 16 because of the concave lens. Object distance is equal to negative 70, the same as before. Our image distance is equal to what? And so when you work it out, 1 over negative 60 is equal to 1 over negative 70 plus 1 over di. So it becomes 1 over 70 minus 1 over 60 is equal to 1 over di. So 420, 6 minus 7 equals to 1 over di. So di is equal to negative 420. What does that negative sign tell you? That the image is not really formed on that side. So what exactly is happening there? The image is not focused over here. These rays are diverging and going away. So basically what happens, because you saw the distance is negative 420, not a positive one, because if it was a positive one, it should have converged somewhere here. Because it's coming negative, that means these rays are going like this. After coming and hitting here, those rays are diverging. That's why it's coming out negative. And where is the 420? 420 is the distance from where these are appearing to come from. Of course, it's not drawn to scale. So these are coming from where? So these are diverging in such a way that to an eye it appears that these are coming from 420 centimeters from that side, from there. You get it? And it's a virtual image. It's a virtual image here. So when you have combination of lenses, this is what you do one after the other. And then, now if you, as I said again, magnification, if you want to find the magnification, do the magnification on the first one, and then you do the magnification of second one, and then just multiply them. So the first one's magnification is 2 times, and the second one takes it and magnifies it 3 more times, then the whole magnification is 6 times. You get it? If the first lens magnifies it 2 times, the second lens magnifies it another 3 times, positive, positive. That means it's going to get magnified all over. So what's the magnification of the first one in this case? Minus di over do. Di. So negative 120 over do. 60. So what's the magnification? What's the minus 2 meaning?
Inverted.
It's inverted. The minus 2 means it's inverted. And since the 2 is a number bigger than 1, it is a magnified image, but it's an inverted image. That's what happens here. And now what's the magnification of second lens? Magnification of second lens is minus di over do for this concave lens. It's minus di is negative 420, so it's become positive 420 over do. The object distance for this is minus 70. So how many times is magnified?
-6.
Negative 6 times. So what is the overall magnification? Positive 12 times. So this whole thing is going to magnify positive 12 times. Get it? So that's what we do for combination of lenses. Questions? No? Good.
12, what?
Hmm?
Just the magnification is 12.
Positive 12, yes. Positive 12 means it is upright. The final image is going to be upright.
So you multiply the
Magnifications. That's why I said the idea is one of them magnifies it to some extent, the other one picks that image and magnifies it further. So you found the two magnifications, just multiply them, that'll give you the overall magnification for the two lenses together. Yeah, so what did you learn from here? The virtual object concept, right? So if rays are coming from somewhere, that becomes a virtual object situation. So can a plane mirror form a real image?
No.
Can a plane mirror form a real image?
No.
Why not? When you look into a plane mirror, what you're seeing is a virtual image, right? My question is, can a plane mirror form a real image? I'll show you how it can form a real image. Go back to the same question that you did earlier. Where did you keep the object? You kept it at 6 centimeters, right? And where did the image actually form? 120. The image is formed 120 centimeters away. So that is where a real image should have formed, right? Now I'm going to put a plane mirror here. I'm going to put a plane mirror there. So if I put a plane mirror there, what will happen to these rays? Now, for the plane mirror, are these coming from a real object or a virtual object? For the plane mirror. These are coming from a real object? Virtual, they're coming from somewhere. I told you clearly, what is considered a real object? Real object. That is a real object. Going, the rays go like that. And what is a virtual object? Rays coming from somewhere and converging like this. So where are these coming from? Definitely not from this side, so which means it's a virtual object. How much is a virtual object distance? Of course, I have to tell you this. Let's say this is 100 centimeters.
Wait, I think I might have switched up my notes. I said real image was like this and virtual image was like that.
Say it again.
I said the real image converges like that and the virtual
Image. I'm talking about object.
Oh, object. Okay, so where it starts?
Yeah,
This is
where it starts. Yeah. For object, real objects. See, you're a real person there. So you're a real object. However, the rays coming from you to my eyes, like that. Like this. Correct? So that's real. Now virtual, how do you identify the virtual thing? This is a virtual. If rays are coming from somewhere, not from a definite place, that becomes a virtual object. Of course, you're not going to get a virtual object straight away from a source. It should be, normally it comes in this kind of situation.
So what would a virtual object be?
For this, for the plane mirror, these rays are not coming from a definite place on this side.
So they don't meet?
No, they're not starting from somewhere. Do you see? Are these starting from somewhere definite on this side? So that becomes a virtual object. For this lens, the object is real because the rays are actually starting from here. But for this mirror, these are not starting from a definite place, but they appear to hit here. So are these rays going to really go there? No. So what is the virtual object distance for this mirror? Negative 20. And what will happen? When they go and hit here, what will happen to it? It just bounces and comes this way and hits here. What distance? 20 from here, because a plane mirror will form the same distance images. Now, is this image real or virtual? That's real. Look, these are really hitting. This one is formed by real hitting of the rays, like that. So that is a real image. Real image. Real object. For the plane mirror, this is the virtual object. For the plane mirror, this is a virtual object. And this is finally, so this plane mirror is forming a real image, but obviously the object is virtual. So if you're standing in front of a mirror, you become the real object, so the image is virtual. But if there's a situation where there is a virtual object situation, then you get image real.
How would that look? 'Cause would you be
So
able
I
to
can
see-
put a screen here and I can get an image. That's basically what it is. I can put a screen over here and I can get the image formed.
So without the screen, you wouldn't be able to see that image, the visual image?
Yeah, you won't see that image in the sense it is converging right there. So if you want to observe it, either you have to go there and observe it with your eyes, or put a screen and watch it.
But if you come in closer, would it all get messed up?
No, it is actually formed there. So if you want to observe it, you have to put the screen at that spot only.
Oh, okay.
Like for example, when you turn on this projector, the image is formed right here, not anywhere else. So if I move the screen here, I'm not going to get a sharp image of the stuff because the image is formed here. So if you want to observe that real image, you have to put the screen right there, or you go there personally. Yeah.
If we put a little mirror right at that real image and bounce it back off the
Yeah.
plane mirror,
Okay. So if you put another mirror here,
yes.
a tiny mirror.
Oh.
If you put a tiny mirror right there, what's going to happen is this becomes a virtual object for that one, and so it bounces back there.
But now is that image on the mirror?
Oh,
A real
and
image?
that depends on where you're putting this mirror.
Okay.
Well, now
So this would be real also.
What?
Let's just destroy our.
This becomes a virtual object for the next mirror. Yeah. So
So now you put a screen there, you can't even see the little mirrors in front of you.
no, but you can always see from an angle.
Can you make the mirror the screen by putting it on the mirror? Like the same
Mirror
as-
cannot be a screen at all.
Well, if you make it project to where it comes to an endpoint right at the mirror.
Oh, at the mirror,
Yeah.
and you put a little piece of paper there. Yes, you should be able to see.
So it'd be a mirror unless you put something in front of it.
Yeah, you have to put something. A mirror itself is not going to display anything because a mirror's job is to just bounce it back. So if you want to see it, you have to put it. All right. I'm taking it, so you should be able to see it. So we're just discussing about combination of lenses.
Yes, they can.
Okay. And next concept. Now remember, when I did mirrors, when I did mirrors, I told you something called spherical aberration, right?
No.
What's
Yes.
no? You're not reviewing material properly. What is the spherical aberration? I even showed that aberration in my cup. Walk around.
It's
Yeah.
Oh, yeah.
A spherical aberration in a mirror is when you have, so this is a mirror. The rays that are narrow, they hit at a certain spot. But the rays that are wide, they hit earlier. Like that. So it forms a kind of a caustic curve, and I showed that one in my cup, walking around. Right? So this is something that happens in a mirror. The problem is the mirror is wide, so a wide mirror will suffer this thing called spherical defect. It's just because the mirror is spherical, that's why. And a way to kind of compensate for this error, aberration, is to make it parabolic. So if you change it into a different shape, you can actually get all of them focused to one spot. And that is what is done in mirrors, like telescopes. Those are not spherical mirrors. Those are parabolic mirrors. They're made parabolic because you want them all to come to one point. Because to observe the skies, you need a wide mirror. And if you take a wide mirror, you're going to have this problem if it is a spherical mirror. And so all the dish antenna and all those things are parabolic mirrors. They are not spherical mirrors. All the dishes that are used for telecommunications, they're all parabolic mirrors because wide mirrors will suffer from spherical aberration. You get it? And that is a defect also in lenses. In lenses, if you use a lens that is pretty wide, what happens is the lens is pretty much correctly shaped over here, but at the end it actually kind of ends with a very large angle. So the prism action over here is a little sharp at the edges, and the middle it does a proper. So what happens is if you use a wide lens, rays that are going and hitting here will converge to one spot, which is the focus. But rays that are going and hitting there will hit like that. And so what's going to happen is that you have multiple places where the focus comes in. So you have multiple foci or foci. So these rays are going to hit here. The wide rays are going to get hit earlier. So what will happen is if you use a lens, pretty wide lens, the image is not going to be clear. Where will you put the screen? If you put the screen here at the very end, you're getting these rays focused, but the other ones will be out of focus. That means it's kind of creating a blurred image. If you put it over here, then the wide ones are getting focused, but the other ones are not. So you're getting image quality defect, right? That is a spherical aberration for lenses. That's called the spherical aberration for lenses. Normally, a spherical aberration for lenses are kind of minimized. You can't just get rid of it, but minimized by not making the angle sharp. And how do you not make the angle sharp is, suppose you are looking for a convex lens of a certain focal length. The lens is supposed to be like this, but then look at the angle there, it's pretty sharp. So instead of that, instead of using one lens, you use 2 or 3 lenses stacked together. So it becomes a combination of lenses. You understand? So the first lens is like that, second is like that, third lens like that. So all of them have small angles. So all of them will do a little bit, and therefore the spherical aberration will be minimized, not completely eradicated. It can be minimized. So in some optical instruments, they put stack of lenses next to each other. Why can't they use one lens like that? Is because they want to get rid of the spherical aberration issue. It happens only for wide lenses. It happens also for your eyes. It happens also for your eyes. When you have bright light, you see things very sharp, right? Have you noticed it? When you have very faint light, you don't see things very clearly. It's very, very common. And what is the reason behind it? I mean, it's blurred. In fact, it is blurred. When it is kind of dimmer light, it's blurred, not very clear. But the moment the lights are put on, it becomes crystal clear, sharp. What is happening there? Now you have to go into the structure of the eye. What is happening what is in your eye?
The lens.
The lens, and what is outside? Outside that lens, there's something called
Cornea?
iris. Have you noticed the iris?
Yeah.
It is something that controls the amount of light that goes into your eye. So it is an automatic, in a camera, there is an iris in the camera too. I mean, if you're taking a manual camera, not an automatic one, you have to physically adjust the iris and then take the shot. Now, if you're taking a picture in a dimmer area, you have to kind of open the iris wide and take the shot. Otherwise, enough light is not coming into the film, right? Now, if it is bright light, you're taking a picture in a sunny atmosphere, you have to reduce the iris like that. Then the picture becomes okay, because otherwise the film will be overexposed. So the film has to be getting some amount of brightness, otherwise it will get overexposed. Now, if the iris is kind of fixed, what will happen is, in bright sunlight, it gets overexposed. In dim light, it will be underexposed, so you won't see any picture. And that's why we have God has created our eyes with iris, not us, basically all animals. And what does that iris do? It actually kind of reduces in diameter and opens up depending on the intensity of the light, depending upon the light. And if you want to observe it, the best thing to do is go to a room which is faintly lit. Go to a mirror, look at your eye, and you'll see your iris is wide open. Because it's dim, immediately your body tells you, okay, it is pretty dim, so open wide, then only you can see things. So it's all open. Now take a flashlight and just shine into your eyes straight away. Not too bright, okay? Not a laser light and all that. Take a flashlight and just turn it on right onto your eyes, but while you're turning it on, keep looking at the same iris. And you'll see as soon as you turn it on, the iris goes shh. It just shrinks like that. Okay? Yeah.
If there's too much light, could it ever close?
It won't close completely. It makes a tiny hole, that's it. Now, if it is too much light, you start doing that. Because if the iris is not closing enough, it hurts. Because too much brightness on your retina is going to be harmful for you. So therefore, the eyelids will start doing the job also, like we start doing that. Because we want to control it by all means. Especially when you get up in the morning, while you're sleeping, it's in a dark room, and your iris is wide open. It's pretty wide open. And as soon as you get up, you turn on the lights, and immediately you do that. You don't, because it takes a little while for that iris to come down. It'll take a little while. That's why you're able to see it. It'll take a little while. And in that little time, it's too bright, you cannot control, and you kind of use your eyelids and kind of close your eyes and walk around like that. And then once your iris is kind of controlled nicely, then you open your eyes and it's fine. And that's what happens in film theaters. In theaters, when you go there, you are going into a room and it's like pitch dark. You can't even see anything. Right? It's dark. Even though there are some lights lit there, compared to from where you walked in, it is dark. And so you can't even see the steps. Where are you walking? But be there for some time and you'll see everything. You'll see everybody in that room. Because this is controlled. Everything is wide open then. And that's why even though the screen brightness is not too much, you're okay with it. It is enough for you to see. So iris does a good job of controlling the intensity. So where is the iris? Iris is right there. So if the iris opens up wide, what happens to these rays coming in? They're coming and hitting at different places on the retina, makes the image slightly blurry. You understand? So in a dim light, all these things are going to hit here. Where's your retina? Retina somewhere here, which is not exactly at one focus. And so your image is... Now when you turn on the bright light, as soon as you turn on the bright light, the iris shrinks and only this part of the lens is used. Only this part of the lens is used, not the entire lens. Your eye lens is not fully used. Only this part of the lens is used. So it becomes now narrow rays. It will have one focus. You are able to get it focused. So that's the reason why bright light makes a huge difference. And not only bright light, you can also do it like this. See, if you make a tiny hole without glasses, if you make a tiny hole and look through the tiny hole, the objects will be very crystal clear. Check it out. Check it out.
In like paper?
No, just like this. Make a tiny hole, which is your dominant eye. Which is a dominant eye. Use the dominant eye. And look at the board and all that. These things become crystal clear. It will be dimmer. It will be dimmer, but it is crystal clear. Check it out.
Why is it?
Because you're using only this part of the lens. You're narrowing it down. You're not using all the lens.
So this is less than even our iris constricts?
It's, yes, kind of. You're limiting it, So basically what is happening is you're limiting that area. And so you're controlling the amount of light that's going from here, from the edges. Yeah. So yeah, those are there are different defects of lenses and eyes and all that. One of them is this. So if these parts are not doing a right job, then you'll have this issue. of not getting. So bright light will make a huge difference. So if I try to read now, this is enough bright light. That's why I'm able to read perfectly well. But if the light is not too good, I struggle reading it because it is terrible. As soon as I turn on my cell phone and just shine the light, it's so crystal clear. I can read it now. Yeah.
So if we can't read something far away, and went like this.
If you do that, it's clear. It's clear. Try it out. In fact, before I did my laser surgery and all that, I used to have reading glasses, and with reading glasses, I'm okay. But when I sometimes go to the shop to get something, say for example some medicine or something, I want to see what is the ingredient in that. So it's tiny. Stuff is very tiny, and I cannot see it because I forgot my glasses. Now, where do I get my glasses? Here it is. So what I do is, if I want to read something that's in very fine print somewhere, I can actually do this and just go like that and keep this close, and I can read it all crystal clear. Yeah, I mean, if you can read things very clear if you go really close, but you have to make it tiny. Yeah. Yes.
I have a question about your laser surgery. My brother's always told me since I was little, or like in the 8th grade, that